Hi there! Today's video will be centered on the construction and installation of the power supply modules for the synthesizer project. We will need one module for each of the shelves, and we will make them so that they can all be powered on from the same place. To do that, we will build one primary module that provides on its panel a power switch and a fuse holder, and then we will build a number of auxiliary modules, one for each of the other shelves of our synthesizer. The auxiliary modules will use the switch and the fuse of the primary module to power up. In my particular case, since I made a 2 shelves rack, I will only need one auxiliary module. Let's get into it. But first, remember that the teamseas campaign is still in progress, and you can still make your donation to help to clean up the oceans. teamseas is a global campaign to raise $30 million to remove 30 million pounds of plastic and other trash from the oceans, rivers and beaches. teamseas is partnering with the Ocean Conservancy and the ocean cleanup charities to make it all really happening. Search for the links to these organizations in the video description below, as well as the link to teamseas to make your own donation. And since you are there, please give me a thumb up, subscribe to this channel, and make a contribution to it too. Hi there! I am Carlo Carrano, and this is Electronics Engineering Made Easy. The schematic for the main and auxiliary power supply modules is the same and is really straightforward. We have seen similar schematics for other projects in this channel. The power supply is capable of providing 3 different voltages, plus and minus 12 volts for the analog circuits and a plus 5 volts for the digital circuits. We can draw a combined 2 amps from the power supply, with a maximum of 1.5 amps for each of the individual voltages. That is more than enough power for all the modules of a single shelf for the synthesizer. This power supply needs a transformer with a primary capable of dealing with the voltage distributed on the power outlets in your country. In USA it will be 120 volts. The secondary needs to be a 12 plus 12 volts AC, which is one of those transformers with 3 wires on the secondary. Usually the center wire, which will be the ground of our circuits, is of a different color than the other 2 wires. The transformer secondary will be connected to U1. The top 2 terminals will be used for the 2 end wires of the transformer, and the third terminal from the top is for the center wire, which is connected to the ground of the circuit. The wires carrying the 12 plus 12 volts AC will go to the AC input of this bridge rectifier, which will provide a positive and a negative output that we will regulate with the remaining of the circuit. The positive from the bridge is connected to capacitor C1, which will remove the variable component of the voltage and will provide a steady DC voltage. I have chosen to use a 1000 microfarad capacitor to get a good rejection to sudden changes in the load. Between the positive and negative electrodes of the capacitor we will find a voltage equal to 12 times 1.41 volts, or about 16.9 volts, which is more than enough to correctly polarize the input of the voltage regulator U3, which is a 7812, that will provide a regulated 12 volts DC at its output pin. This voltage will be further treated with another electrolytic capacitor, C2, which will further contribute to help absorb sudden changes in the load. Diodes D1 and D3 are there to help the current to find a way to discharge the capacitors once the power is shut down, as well as to prevent damage to the circuits. The output from the 7812 goes directly to the output connector pins 1 and 2. Similarly, capacitor C4 takes care of filtering the negative DC voltage. U4, a 7912 regulator, will provide the minus 12 volts DC, and C5 will provide further filtering, like C2 on the positive side of the circuit. The negative side of this circuit is completed with diodes D6 and D7, and the DC voltage is brought to the output connector on the pins 7 and 8. The plus 5 volts DC is provided by this 7805 regulator, which takes the output from the plus 12 volts DC through the two 2.7 ohm resistors here. The reason for these resistors is to protect the 7805 from burning out. In fact, an input voltage of 12 volts with an output of 5 volts at 1.5 amps would cause a dissipation of about 10 watts on the IC, which could be damaged by that. The resistors will take care of absorbing that power by reducing the input voltage on the 7805. The more current will be requested at the plus 5 volts output of the regulator, the less voltage will be at its input, and therefore the dissipation of power of the 7805 will be limited. Note also that although we could take up to 1.5 amps from the plus 5 volts output, that current has to go first through the 7812, and therefore we cannot drive more than a combined 1.5 volts from the plus 12 and the plus 5 volts outputs. The plus 5 volts at the 7805 output is made available through the output connector again, this time on pins 3 and 4. Pins 5 and 6 of the same connector share the common ground for all three voltages available. And finally, there are 4 more connectors on the schematic. U2 is used to provide a ground connection to the copper shielding walls of the shelf. The remaining 3 connectors are used to connect 3 voltmeters on the module panel to keep an eye on the voltage available on each rail. If we see conspicuous changes to the voltages on these voltmeters, we will know that something is wrong and we will be able to promptly intervene. For example, if we add a new module on the shelf and one or more of the voltages goes to 0, we will know that the new module has a short circuit in it, and so we would power down the synth, remove the new module and fix it, and this before the internal safety circuits of the regulators would give up. To avoid issues with the dimensions of the modules, I tried to do some sort of standardization. I basically prepared a template from which I can 3D print any sort of module by simply adjusting some parameters and describing the position of the holes I might need to hold in place the PCB or for the components of the module front panel. This is the template module, which I called Standard Module. The first thing we need to notice is that my 3D printer is not big enough to print the whole thing in one shot. I therefore had to divide the print in 2 parts, the body of the module and the wings that are used to secure it on the shelf. The parameter named Print Choice is used so that I can describe the whole module in a single file, but I can choose which part to print depending on its value. For example, right now the parameter is set to 1, and 1 means that I want to print the body part. But if I set the parameter to 0, then I signal the software that I want to print the wings, like that. These wings, once printed, will be attached to the top and bottom of the body with some glue. 2 more parameters, here on the top part of the file, are named Depth and Width. They define the depth of the body of the module, which will depend on the size of the PCB that has to fit in it, and the width of the front panel, which mostly depends on the amount and size of the components that need to be put on the panel itself. These 2 parameters are not the actual dimensions, but rather they are just multipliers that are applied to the actual base dimensions, which are defined along with other constants in this section here. Let's move back to the body selection now, so I can show you how the dimensioning parameters work. Let's start by setting the depth to 2. You can see that now the depth of the module has doubled, so that the side wall of it can hold a bigger PCB than the previous one. And now let's change to 2 the width. See now, the front panel has become much larger, and so it can host more potentiometers, jack connectors and other stuff. If we now look at the wings, we can see that their size has been automatically changed too, as well as the number of holes to screw the module on the rack. All the measurements have been defined in such a way that the height of the modules fit perfectly the height of a single shelf, while the basic width is such that we can put up to 18 modules on the same shelf. And of course, if you use modules with double width, you will be able to put only 9 modules on the same shelf, and so forth for any other combination. Based on the dimensions of the shelf and on the plate of my 3D printer, we can actually use depths up to 3 times the base depth and widths up to 4 times the base width. Once the width and the depth have been chosen, we can add the necessary code to this section to describe the size and position of the holes on the front panel. And then we can use this other section to define size and position of the holes to hold in place the PCB of the module. Here is a template module which I printed for you to see the results of all that code. I already glued the wings to the body so you can see the final effect. Remember that playing with the dimensional parameters, I can change the width by doubling and tripling it. Same thing goes for the depth, so I can obtain a surface big enough to host the PCB of the module. Let's now see how I modified the file to create the main power supply module. Here you can see that I defined a depth double the size of the template and a width that is 1.5 times the base width. This one is the code that describes the holes on the front panel. The first 3 holes are for a set of 3 voltmeters, which are supposed to check that the power supply is providing the correct voltage for the modules on the shelf. Changes in the voltages are an indication that there are problems that need to be addressed. The other 2 are instead the holes for the power switch and for the fuse holder. It is always better to have a fuse that protects the high voltage section of a system, so that in case of an overload or a short circuit, the fuse will burn, and that will protect all the powered electronic circuits. And finally, here is the description for 4 holes used to screw in place the power supply PCB. You can see the actual holes here on the side of the body. Here is the printed module case, with the wings already glued to it. You can actually see the glue I used since the plastic is relatively transparent. The depth is adjusted to host the power supply PCB, which will be anchored through these 4 holes. Here are the 3 holes for the voltmeters, which will measure the 3 voltage values, the plus 12 volts, the plus 5 volts and the minus 12 volts. And finally, there are 2 more holes. The first one is for the fuse holder, so it is easily reachable to eventually replace the fuse. This fuse will be traversed by the current powering all the shelves at the same time, and so it has to be sized accordingly. The second hole, instead, is the hole for the power switch, and that will take care of switching the power on and off for all the shelves at the same time. Here is the design of the auxiliary power supply module case. As you can see, it is identical to the one made for the main power supply. The only difference are the missing holes for the power switch and the fuse holder, since this unit will use the ones from the main power supply. And here is the printed case, again with the wings already glued to it. I originally designed the voltmeter holes to stage units that had both a voltmeter and an ammeter in them. Later, however, I decided that the voltmeters were more than enough, but I was then left with big holes. Rather than redesigning the case to reduce the size of the holes and print them again, I decided to leave them alone and print instead some adapters, designed explicitly for the voltmeters I wanted to use. This way, actually, if I later change my mind again, I will just have to print further adapters for the voltmeters of choice. In the end, my indecision ended up being a good thing, because I was able to create a more flexible design. Here is the OpenSCAD file with a 3D rendering of the adapters. The front will be flat with the voltmeter displays, and the back is shaped to be able to fix the instrument in place. They are very small, as you can see. I had to print a total of 6 adapters, 3 for the main module and 3 for the auxiliary module, and you can see how they fit in the big holes of the front panel perfectly. The other thing I decided to do is painting the front panels of all the modules that I will be making. The paint will make the decals for the front panel stick better to it, since the PLA I use with my 3D printer does not work very well with the decals. I also decided to go with white paint for all the modules, so there will be a better contrast with the decals. To spray the paint, go with a light coat first, so it will not start dripping, and once dry, repeat 2 or 3 times to have a good layer of paint. Once the last layer of paint is dry, we can add the decals, and then we can spray 2 or 3 more layers of transparent paint on top to prevent the decals from scratching or detaching. To put the decals, the procedure is very simple. I'm sure you have seen it several times in other projects of mine. First, prepare the design with your preferred editor. Then print it on decal paper made for laser printer or for inkjet printer, depending on what you have. Then, cut the pieces you need in just about the right size. Put the pieces in water to lose the glue and slide them in place and let them dry. A transparent spray paint will prevent scratches and attachments. Always go with a thin layer at a time and spray several layers. The assembly of the electronics is relatively easy to do once you have the PCB for it, and you can either order the PCB online to one of the several companies that make them for you, or you can use my method for creating a PCB using a laser printer, which I explained in a recent video. Start by putting in place all the connectors, those for the voltmeters, the one for the power rails, and the ones to connect the circuit to the transformer and to the ground. Make sure that you put the connectors in the right direction to respect the polarities. In my case I made a mistake actually with the one for the power rail. Once I realized that, it was too late to change it without possibly damaging the PCB, and so for that I had to rearrange the cable that I wanted to use so that the polarities were respected. After the connectors, solder the bridge rectifier. The thick wires of the rectifier tend to dissipate all the heat from the soldering iron. Increase the temperature and cut short the wires to minimize that and ensure that the solder melts correctly. Then you can connect all the diodes, and then the 2 high-power resistors. About the resistors, I found that the holes for them were too small. I have probably used a wrong type of resistors when I designed the PCB, but rather than enlarging the holes, which would have caused a problem interrupting the connections between the 2 layers of the PCB, I decided to bend the wires and solder them on the same component side. Next time I will need to be more careful when designing the PCB. Oh well. After the resistors, put in the circuit all the electrolytic capacitors, being careful in respecting their polarity, which is well represented on the PCB silk layer. Electrolytic capacitors need to be polarized correctly, because otherwise they could even explode when a voltage with the wrong polarity is applied to them. I can tell you, when a capacitor like that explodes, it is not nice. It spreads around all the liquid electrolyte inside of it, not to mention that it can be dangerous, especially if your eyes are not protected. Lastly, take care of the voltage regulators. Before soldering them on the board, however, attach them to a heat sink, using also some thermal paste in between to decrease the heat resistance. When you do so, make sure that the heatsink does not touch any other component on the PCB, especially the capacitors, since the heat produced over there could melt the insulation around the capacitors and cause a short circuit. Once both circuits are built, the one for the main power supply and the one for the auxiliary, proceed with testing them both. Since there is high voltage running on the transformer primary and there are unprotected cables lying around, I tried to minimize the risk of shock by building this testing platform on a piece of wood. The power cord is attached to 2 connectors of a snappable pin header. The cable is held in place with one of those cable ties you hammer in place, so it will not detach from the pin header if pulled. The transformer primary is connected to the other end of the same pins on the header, and of course this is the actual transformer that will power up the whole shelf. The secondary of the transformer has 3 wires. The white wires provide the 2 12V AC, while the black wire is connected to the center of the secondary, which is our ground. I attach these 3 wires to a second snappable pin header, and then I use 3 more wires to connect the other end of the pins to the appropriate places on the connectors of the PCB. The 2 blue wires carry the 12 volts AC, and the white is again corresponding to the ground. Then I powered up the circuit by plugging in the power cord into an outlet, and then I used the multimeter set to AC voltage to make sure that the transformer was actually powered up. Then I checked that I also had the correct voltage on the secondary. Last, I set the multimeter to read DC voltage and verified that the correct DC voltages were generated on the PCB. To make it simple, I first attach the common probe to the ground connector, and then I use the other probe to move around to take the measurements. Be very careful when you take these measurements. Don't touch the high voltage wires or you could get electrocuted. As you can see, I was able to measure all the voltages correctly. First the plus 12 volts, then the plus 5 volts, then I verified the ground pins were connected in the right place, and finally I measured the minus 12 volts. And of course, I had to repeat this procedure also for the second PCB. Now I had everything ready for the final assembly of the modules themselves, and then the modules on the shelves. To assemble the modules, start by putting the voltmeters on the front panels. I have 2 sets of digital voltmeters, one for each panel, and for each voltage I have chosen a different display color. I had a red for the plus 12 volts, a blue for the minus 12 volts, and a white for the plus 5 volts. So first thing to do is to take the adapters and attach the voltmeters to the adapters. Then we can fix the adapters to the panel. Let's start with the first set of 3. Here is a blue display which will be attached like this on the adapter, with a couple of drops of glue. This way the display will be flat with the front of the adapter. But before I forget which color is which, I'm going to write down on the back of each adapter the corresponding color of the display. So this is the blue one, this is going to be the white, and this is going to be the red one. Let's start gluing the blue display now. For that I am going to use a cyanoacrylate glue, which will set relatively quickly. First a little cleaning of the pods, since there are traces of cardboard from when I painted the adapters. Then a couple of drops of glue, one on each side. Then I can position the voltmeter. And then some masking tape to prevent the voltmeter from moving while the glue sets. And now let's do the same with the white one. And finally the red one. Same thing needs to be done for the other set of voltmeters and adapters. Then we wait until the glue is set, which is about a couple of hours just to stay on the safe side. While waiting for the glue to set, let's attach the standouts to the sides of the module cases. These are the ones that will hold in place the PCBs, and for that we will need to use a screwdriver and pliers. First one done, then the next, the other next, and the last one. And then we will do the same thing for the other module. At this point we can attach to the front panel of the main power supply module the switch and the fuse holder. Since the fuse holder will be subject to torsion when turning the cap to insert or replace the fuse, I added some glue on its nut on the back side of the panel so it won't move anymore. While there, we can also wire the fuse holder and the power switch. The switch and the fuse holder will need to be connected in series, and they will also go in series with the hot wire from the power outlet. These are the 2 pins of the switch that will be shorted when the switch is in the on position, and so they are the ones that we need to use. Put a wire between this point of the fuse holder and this point of the switch, so the 2 components will be in series. Then connect this pin and this other one to this wire, which will be basically the one that will be used in series between the transformers and the power outlet to open and close the circuit. so we can turn off and on the whole synth. So let's do that. First, I'm cutting a piece of wire of the appropriate size for the connection between the switch and the fuse holder. I will also need some shrinking tube to insulate the connections to prevent electrocutions. Let's strip some insulations from the wire. And since the wire is thick, I am separating the strands in two parts, one that goes inside the hole of the switch pin and the other one that goes around it, and then some solder will keep everything together forever. Now it is time to put the shrinking tube on the soldering point. Use the heat gun to shrink it in place, then insert another piece of shrinking tube to insulate the other soldering point, attach the wire to the fuse holder and solder it, then slide the shrinking tube on this new soldering point, and finally use the heat gun to shrink it and secure it in place. Ok, now it's time to connect the other wires to complete this part of the circuit. So, separating the wires, stripping the tips, inserting a piece of shrinking tube on the first wire to insulate the corresponding soldering point, soldering the first wire, add a shrinking tube to the other wire, soldering it on the fuse holder pin, sliding the tube on the new soldering point, and now we can use the heat gun to shrink both tubes. Here, done! We will use this cable later on to switch on and off the power on the transformers, both of them, which will be located directly inside the rack, one for each shelf. Ok, now the glue is practically set, and so we can proceed with attaching the adapters to the front panels of the power supply modules. I will do that again using some glue, which I am laying on the edges of the adapters from the inside. This is the red voltmeter, so it will go on the top. Now let's clean some excess glue. And I'm gonna add some masking tape to hold in place the adapter until the glue sets. And then I will do the same with the other two adapters, putting the white voltmeter in the center and the blue voltmeter on the bottom. And this is the final result. Now I will do the same with the other module, and then we will have to wait a little bit more until the glue sets. Ok, the glue is now set, and we can remove the tape that was holding the voltmeters and the adapters in place. Let's now take care of the connectors for all these voltmeters. These voltmeters come in two different wiring modes. This one has only two wires, a red one and a black one, to provide the power supply, and the measured value on this voltmeter is the power supply voltage itself. This other one instead has three wires, a red one, a black and a yellow one. The red and the black are for the power supply, while the yellow is the one used to make the measurements. Both kinds of voltmeters have a wide range of possible power supply voltages, and because of that I can remove the yellow wire from this particular one and connect its pad on the PCB directly to the one for the red wire. This way the 3-wire voltmeter will work exactly as the 2-wire one, and we will be able to measure directly its own power supply voltage. After that, I will attach to each voltmeter a 2-pin connector that will be inserted in the corresponding spot on the PCB. These are the pins and the connectors that we are going to attach to the voltmeter wires. We start by crimping the pins to the wires. For that we follow the exact procedure I explained in the previous video of the series, where we prepared the connectors for the power rails. The goal is to be able to connect and disconnect at will the voltmeters from the power supply PCB, so that we can easily remove it in case of a repair. Once all the pins are crimped to the wires, we need to insert them in the connector shells, and of course we need to make sure that we put them in the right order, otherwise the voltmeters will not work because they will be powered up with the voltage polarity switched. Looking at the PCB, we can figure out which side is supposed to be the positive one, and then we can insert the pins with the red wires in the position of the positive voltage. All the connectors will have to be assembled the same way, and the whole procedure needs to be executed also for the other module. And now it is time to attach the PCBs to the module cases. Make sure you orient them so that the connectors for the voltmeters face the back of the front panel, while the other connectors face the back of the module, so it will be easier to put the wires from the transformer and to attach the PCB to the power rail. Once the PCB is secured to the panel, we can attach the voltmeter connectors to it and route the cables so they won't be on the way. It is time now to add a fuse to the main power supply. Remember that the fuse must handle the current from both the transformers of the main power supply and auxiliary power supply. Since each transformer has a power of about 50 watts, for both of them we will have a maximum power of 100 watts. With a voltage at the outlet of 110 volts, we will therefore need a 1 amp fuse. Of course, if you live in a region where the voltage at the outlet is different, you'll have to use a different type of fuse. Use this formula to calculate it. Current of the fuse equals the power of all the transformers together divided by the voltage at the outlet. And then round up the result to the closest available value of fuse that you have available. The transformer that goes on the shelf with the auxiliary power supply will need to be connected to the shelf with the main power supply, since the power switch in that shelf will act on both the transformers. Since the primary wires of the transformer are too short to do that, I will have to make them longer so they can reach the other shelf. To do that, I am going to attach to the primary wires this piece of 2 wires scrap cable. I am also going to use some shrinking tube to insulate the connections to prevent any possibility of getting electrocuted. One more time, you need to be very careful when working with high voltages, because they are dangerous and possibly fatal. If you are not comfortable working with high voltages, please seek help from a friend that knows how to handle them. The best approach in this case is to wrap around the wires and then solder them together, so they will no longer be able to separate. Before doing that, of course, don't forget to insert the shrinking tube, since after the connection is done, you won't be able to do that anymore. Once the first wire is soldered, repeat the process with the second wire. Then, slide the shrinking tubes over the connections. And then use the heat gun to shrink them in place. Now, for the sake of increased protection, I am going to wrap the 2 tubes in insulating tape, just in case the tube breaks. And finally, I put another piece of shrinking tube over the whole thing to make sure that the tape won't detach over time. And now the transformer is ready to be installed on the shelf of the auxiliary power supply. I did not add a wire also to the primer of the other transformer, since it is close enough to the main module and so it doesn't need it. Let's now start the assembly of the modules on the shelves of the rack. The first thing we need to do is to electrically connect the upper shelf and the lower shelf shieldings. For that, I am going to use a wire that I already prepared with connectors at the 2 ends that can be screwed directly to the walls of the shelves. I will fit the wire through the hole I prepared when I assembled the rack itself. Now, each end of the cable can be screwed on the wall on each shelf. However, I will also add another piece of wire to each side that will connect the shelf shielding with the ground of the power supply PCB of that same shelf. When you do this, use a screw that is not too long, otherwise it will come out of the wall on the external side. Here, like that. The bottom shelf will be done the same way. Well, almost. Since this is the shelf with the main module, this is the one where the power cord enters the rack. The power cord has 3 wires. The ground, which is this green wire, this one with a white labeling, if you can see it, which is the hot wire, and this other one, which is the neutral wire. We want to connect the ground wire from the power cord also to the shielding to have a true ground electrical connections of the shielding and the ground of all the circuitry that we will put on the rack. This is a very important step, because if the whole synth is not truly grounded, we will always suffer from possible noise at the frequency of the AC power supply, like the 60 Hz in North America and the 50 Hz in Europe. And so on this shelf, we will have to screw to the side wall 3 wires instead of 2. Oh, by the way, remember to make a knot on the power cord on the inside of the shelf so it cannot be pulled out from the outside. And done. And now it is time to mount the transformers on the 2 shelves. I am going to connect first the transformer on the top shelf. It will be held in place by a couple of screws in here, right behind the power module. This is the cable from the primary that goes to the lower shelf, so we need to pass it through the same hole as the ground cable. I put the transformer with the primary wires against the wall and the secondary toward the outside of the shelf, to facilitate the connections of the secondary to the power supply PCB. Let me now get the 2 screws and put them in place. To make sure that the screws don't get loose over time, I am also putting an elastic washer on them. And now that the transformer is in, let's hook up the auxiliary module and fix it on the shelf. The module needs to be connected with a 8-pin cable to the power rail, which I just made. Look at the video on the power rails to see how to make one. This one needs just to be longer than those to be able to move around the module before fixing it to the shelf itself. And always make sure that you are connecting all the wires in the right order to prevent reversing the polarities and the voltages. Now we need to connect the ground cable to the appropriate connector on the board. And finally we can connect the transformer, the common wire first, and then the 2 hot wires for the 2 12V AC voltages. Once all the wires are connected, we just need to position the module on the far left of the shelf and lock it in place with a couple of screws. And here is how it looks like once the module is fully installed. And now we can move to the other shelf, which will be assembled slightly differently since it is the one that hosts the main power supply module. So first we install the transformer. Now, since we need to make connections between the 2 transformers and the power switch, I am going to use this header to safely connect all the wires the right way. To fix the header, I will use two screws which I will first partially screw into the header itself in the two holes made exactly for that. Once the screws come out from the other side of the header, I can continue driving them in after laying the header on the back panel, so the screws will hold the header on it. Here, done. And now I can screw in the wires from the power cord. I'm attaching the hot wire to the side labeled in black on the header. The neutral wire goes to the other end of the same side. And now it's time to connect the wires from the power switch and the fuse holder coming from the main power module. One wire goes to the center, on the same side of the power cord, and the other wire goes along with the hot wire connection that can be done from the other side of the header itself. While making these connections, make sure that the copper wires go entirely inside the header with no exposed parts, and make sure that no exposed parts touch the shielding of the shelf, otherwise touching it will get you electrocuted. Not to mention that you could put in contact the hot wire and the ground doing so, causing a strong spark and the trip of the safety switch on the electric panel of the house. Once all this is done, we can complete the circuit by connecting the wires from the two transformers between the neutral and the wire in the center coming from the switch. And this is the schematic of what I have just done. Here on the left is the power cord with its three wires. The ground wire goes to the synth ground, the neutral wire goes to one end of both transformers, the hot wire goes to the other end of both transformers through the power switch, which can therefore turn on and off the power to the transformers. To stay on the safe side, I decided to test for continuity between ground and each of the wires that transport high voltage. We of course don't want any continuity between the two. And so here I am, checking that everything is alright. And so it is, there is no problem of short circuit between the power wires and the ground. So now the only thing that is left to do is to connect the ground wire and the transformer wires to the main power module. Starting with the ground wire, and now the transformer. First, the center of the secondary, which is basically the electrical ground of the low power circuits, but also connected to the common ground. Then the two white wires that transport the two 12 volts AC voltages. Last thing we need to do is to connect the cable with the 8-pin connectors to bring the power to the rails. Ok, now all the connections are done, and we can put the module in its position in the rack. And now it is time to see if everything works fine before fixing the module in place. For that I have to plug in the power cord into the outlet. And now I can operate the switch to turn everything on. Yay! Look at that! Everything is within 1% of the expected values, which is exactly within the specs of the voltage regulators. We have the plus and minus 12 volts, and here too plus and minus 12 volts, and the plus 5 volts for the digital circuits. Now we can put the screws in and fix the module in place. So let's do that. First the one on the top, without tightening it up, and now the one on the bottom. And now we can tighten both up. The last thing left to do is to test the voltage along the power rails. To do that, I created this cable. The 4-pin connector can be inserted in any slot on the rails, and we can test the voltage on the other end of the wires soldered on this piece of perf board to prevent them from touching each other. So, powering up the system. Then inserting the connector in a slot, and checking the voltages one by one. Here is the plus 12 volts, here is the plus 5 volts, and finally here is the minus 12 volts. Let's now check the power rail on the other shelf. Plugging in the connector, checking the plus 12 volts, which seems to be fine, then the plus 5 volts, and finally the minus 12 volts. Okay, everything is fine, and so now the rack is ready to host any other module that we will build for this synthesizer. Here is a view of the whole rack with both the installed modules, the auxiliary power supply and the main power supply. Installing any other module will now be much easier, because the only thing we have to do, after building them, is to plug them into the power rail and fixing them on the shelf with some screws. No other cables will be necessary, as all the connections between one module and the other will be done through patch cables with jack connectors, as in the classic versions of any analog synthesizer. And this concludes today's video. If you liked what you have seen and would like to continue watch my videos, don't forget to subscribe and to click on the notification bell, so you will be informed automatically when new videos come out. And of course, don't forget to give me a thumb up. In the meantime, I'll see you in my next video, and as usual, happy experiments! Oh, wait! Don't go away yet. Before ending the video, I need to mention one more time Teamseas. The fundraising is still in progress, and it will end at the end of the year. So we still need your help to accomplish our goal of removing 30 million pounds of plastic and other garbage from the oceans. So please, consider making a donation to the organization. Every single dollar counts. Links are in the description below. And please, consider also to donate to my channel, so I can continue my work of divulging electronics to the masses the easy way, the eleneasy way. And now, for real, happy experiments!